All right. Good morning and welcome to the 2016 workshop. Before we get started with the first talk given by Serena Debeer on the introduction of coordination chemistry, let me make a few quick remarks. So every workshop is a little bit different and unique, and I think this one is unique in the sense that we have a greater teacher to participant ratio. I think we have about 80 teachers and I think 70 or 75 participants. Before that it was roughly 48% teachers. So more teachers. The format is slightly different. We do always lectures in the morning and labs in the afternoon. You might yourself try to get oriented during the coffee break, during the lunch break, where things are in the lab, because we want to start on time. I don't know what the program really says, but we should have a roughly 10-minute break in between the two lab sessions. I'm not sure whether the second one says 4 to 6 or 4:10 to 6:10 or 4:15 to 6:15. Let's make a roughly 10-minute break so you can go from A to B, because some of the things are in a different building, different floors, so no one gets lost. You can grab a coffee. Posters, they will be set up. If you take 2 flights up, if you go out here, then you end up on the bridge. The posters the boards are being set up right now. You can bring your poster. If you don't have it today, you can go back and grab it during the lunch break. You can set it up. First poster session is on Sunday, second one on Wednesday. If you check your name tag, you will see that there is behind that, there is a small little ballot. Keep that. You can sell it, I understand, because we will be voting on posters, and you all have a vote to select one poster you like, and then we will see where this takes us. We will figure out the rest as we go. Other things, I think we have. Am I missing anything important right now? Coffee is outside, food is outside. Tomorrow there's not going to be any breakfast in the dorms. We know that by now. There will be bagels and more food stuff. Well, there will be proportionally more bagels coming tomorrow morning. And so you don't need to sit here hungry. If everyone should have access to Dropbox, I think. Nothing got deleted. Very good. If you have problems downloading files, let us know. Of all the various methods that require downloading things, probably the DFT part with Orca is the most tricky one. That doesn't start until, I think the first time is not today, it's tomorrow. If you have problems installing that, you should probably contact the DFT teachers. Where are they? So there's Casey, and there's Vijay, and where's Agi Silaos? Back there. So these are the DFT teachers. If you have problems installing that program on your computer, you might want to check with them. Well, then I don't want to talk anymore and introduce. And so the first talk is going to be an overview to set the pace and over this whole field of bioinorganic chemistry. Frank Nese gave it the last couple of times, and this time Serena is going to tell us about this. Thanks, Serena.
Okay, can everyone hear me okay? Yep, great. Normally it's not a problem. So it's not entirely an intro just to coordination chemistry that I'm going to be giving this morning, but really a review of probably your undergraduate inorganic chemistry that I think is useful for you to remember this week. I guess, though, before I start, just for my own information, by a show of hands, how many of you would consider yourself either a biologist or a biochemist? Okay. So hands down. How many of you consider yourself more really chemists? Chemists? Okay. And any physicists out there? I know there's at least a couple from... Okay, good, good. So for some of you, maybe who are more biologically oriented or maybe even more physics oriented, this might be some new material, and for the rest of you, this is going to be a relatively fast tour through your undergraduate inorganic chemistry. And of course, we're doing this in part. Let's see. Now my advancer is not working. I was about to blame Julian. He was the last one to use it. But of course, the reason that we want to sort of do this overview is really to understand how basic concepts in inorganic chemistry fit in the broader picture of bioinorganic chemistry. And as most of you probably know, roughly a third of all proteins contain metallocofactors. And here I've picked just one of my favorite two-component protein system, the nitrogenase protein. And I'm showing here, obviously, the entire 250 kilodalton MoFi protein, as well as the iron protein. And then inside of it, the required metallocofactors. And so when you look at this picture, you kind of immediately can self-identify. If you focused first on the left-hand side of this, then you are the biochemist in the audience. And if you're squinting to see what the cofactors are inside, you're obviously a chemist. And if you think all of this looks far too complicated for anything you could truly understand, then you're obviously a physicist. So for us, though, really wanting to gain understanding of geometric and electronic structure, as helpful as crystal structures are, they, of course, don't really tell the entire story. And so it's obviously a theme that you're going to hear over and over again this week, is that spectroscopy really provides a route to understanding the changes that are occurring in these active sites, so we really can start to get insights into how they actually function. And so as a chemist, of course, I tend not to focus so much on the protein, but I tend to zoom in on the active site. And this is normally what I find personally most fascinating about bioinorganic chemistry. Now, for me, in my own PhD, I spent a long time working on blue-copper proteins. And this active site actually is the active site of plastocyanate. It's a blue-copper protein whose main job is just to do electron transfer. So it cycles just between copper 1 and copper 2 oxidation states, and it does that very well. And the reason it does it very well is because this active site, even in its copper 2 form here, doesn't maintain the geometry that we would normally teach you in coordination chemistry. So for every coordination chemist, we think that a copper 2 active site should go D4H. And in this protein, that doesn't happen. The general idea here is that lowers the reorganization energy, and it makes this protein able to do facile electron transfer. But to appreciate in many ways the beauty of what biology does, we have to understand what's normal for chemists and what's not. And so that's kind of one of the themes that I hope that you pick up from today's talk. Now, there are a number of other beautiful examples of active sites here that I just want to briefly comment on. This is the 4-manganese calcium containing active site of the oxygen evolving complex of photosystem 2. This is the site responsible for photosynthetic water oxidation. And it's a site for which the structure has been a subject of intense debate. The early crystal structures were damaged, and there were completely different proposals from XFs. There were completely different proposals from the same groups doing XFs. In fact, there were different proposals using the same XFs from different theory groups. And what recently has been revealed from a combination of different spectroscopic methods is, in fact, that many people were right. The strange thing about this structure is it can exist in this cubane-like structure, and it can also form an open cubane. It's a structure that has some dynamics that are likely important in the mechanism, but it's something that we as coordination chemists don't intuitively know how to engineer. I will say, however, though, that coordination chemistry has almost caught up to biology, and that it was last year that the Zheng group in China actually reported a structure that can actually undergo this kind of conformational change. And so again, inspiration taken from nature. There are some things in nature, though, where we've yet to be able to really mimic the coordination chemistry. This is the proposed active site of methane monooxygenase Q. This is the intermediate responsible for abstracting an H atom from methane to form methanol. Now, based on a combination of different spectroscopy, this is thought to be a diamond core with a really short iron-iron vector. Now, while synthetic groups, like Larry Kay's group at Minnesota, have been able to make diamond cores that are high-valent, they have longer iron vectors, and they actually can't do this reaction. And so this is a cofactor that continues to inspire and raise questions. Now, in all of these cases, it's the amino acid side chains that provide the ligands. That's our coordination chemistry. In other cases, though, biology can't achieve the reactivity it needs only using the amino acid side chains. And in those cases, biology synthesizes a number of really beautiful cofactors. And here are just two examples of that. Here is the porphyrin site in a P450 active site. And again, one of my favorites, the FeMoco active site of nitrogenase. And as probably many of you know, this has 7 irons, a molybdenum, a central carbon, and it's all bridged by sulfur. And I can tell you that early on, when our group using valence emission first reported this central carbide, I actually got a phone call from a very prominent organometallic chemist who simply told me this complex can't exist. And so this is, again, something that just highlights really the important synergy that needs to happen between the bioinorganic side and the more classic coordination chemistry. So how are we going to do that? We're going to do that using a variety of spectroscopic techniques, many of which you'll be exposed to this week. This is, of course, methods that allow us to probe the interaction between our active site and a very varied wavelengths of light. And so we're looking at everything from the radio waves, which include NMR-based methods or pulsed Endor-based methods, the microwave region covering EPR, vibrational methods like IR and Raman, UV-Vis, MCD and CD, as well as X-ray methods, which I'll be presenting tomorrow on some of the more non-traditional and advanced X-ray methods we can do, and also Mossbauer. And I realize that even this full electromagnetic spectrum doesn't cover all of the methods that you're actually going to be using this week. I know that later this week, Nikolai Lennart will talk about NRVS, which effectively combines the Mossbauer resonance in order to get vibrational data. And I think this is a growing sort of trend to use two-dimensional probes in order to maximize the insight we can get. That's something I'll also focus on in my X-ray spectroscopy talk tomorrow. But in general, as I said this morning, and I know it's early morning, and to say, oh, I'm going to review your undergraduate chemistry, people are thinking, damn, I should have slept in. So I'll do my best to try to keep this entertaining. But what we'll do is we'll walk through just the very basics of coordination chemistry, and first talk about the early concepts that came out of crystal field theory. This is really a theory that is based just on electrostatic repulsion. And being in the synchrotron world, most of my physics colleagues still use just crystal field theory, so we'll talk about that. But I think in chemistry, we know that crystal field theory breaks down in many ways, and this is why ligand field theory and MO theory are very useful tools. Although, again, it's important to point out these are in no way ab initio-based methods. They're simply models that help us think about our systems. And from there, we'll turn to sort of how we use these concepts in spectroscopy. An important part of that is transitioning from the MO picture that as chemists we're very happy with to a picture of states. And in this context, I'm going to cover spectroscopic selection rules. Selection rules for, broadly speaking, what I'll refer to as ground state spectroscopy or excited state spectroscopy. And I think this is important. And understanding those selection rules sometimes is a useful reminder of why, when you focus too much on one spectroscopic method, you may forget about a state-based picture, and that's something I want to remind you of. And then we'll talk about how you determine allowed transitions. I'll primarily focus on UV-Vis for this talk. Other speakers will cover other regions, but I'll try to give you a global picture of how these selection rules translate to various different methods. Okay, so the sum up for this is really from my first PhD student, Chris Pollock. Yes, who has actually told me on more than one occasion, and in fact, unbeknownst to him, I got him to repeat it yesterday in email, that effectively everything he needed to know in grad school he learned in Chem 410. So not everyone knows what 410 is, but you can make the leap. This was the undergraduate inorganic chemistry course. Chris was my TA at Cornell. And here he is actually at a beamline at the Cornell synchrotron, actually putting concepts in 410 to work, collecting valence emission spectra that you're going to hear about tomorrow. But let's move on from that and actually talk about coordination chemistry and the very simple concept really of why coordination complexes actually form. And so really the sort of general concept we want to take here is when you looked at all of those protein active sites, they of course all had a metal center. And that metal center of course is our Lewis acid, what I'm denoting here as my Mn+. And all of my ligands from the amino acid side chains or from the porphyrin, these of course are my Lewis bases. And that of course is what biology is using, but in a very simple picture, I'm just going to abbreviate these ligands as L when they're neutral or X when they're an anion. And here I'm taking my metal ion, I'm interacting it with 6 ligands, and the important thing, of course, that happens here is a coordination complex actually forms due to stabilization of the ligands. And so the part of the picture you want to actually sort of focus on here is the electrostatic attraction of those 6 ligands. Now, conversely, what happens is that the metal is actually destabilized. So we have destabilization of both the core orbitals as well as the d orbitals. And because of that destabilization of the d orbitals, we actually end up splitting them. And that splitting is referred to as a 10dq parameter. And we'll focus on that more throughout this talk. But of course, when we talk about coordination chemistry, when we're seeking inspiration for something that actually relates to our bioinorganic chemistry, we of course need to think about the types of coordination compounds we can form. And so in the language of coordination chemistry, we're typically referring to the actual denticity of a ligand. And so for many ligands, they're actually just monodentate ligands. These are, of course, things like the halides, like fluorine, bromine, chlorine, and iodide, as well as oxide or sulfide that all could have monodentate-like coordination. In addition, we can form different kinds of chelates, so bidentate chelates like ethylene diamine, or more sophisticated tridentate and tetradentate chelates like you see in triethyltriamine or in porphyrins. Okay? And of course, these of course have direct analogies in bioinorganic chemistry, but instead of having these classical coordination ligands, we instead have amino acids that are providing the ligands. And here, I'm just showing some possible amino acid side chain donors you could have, nitrogen donors that could come, for instance, from histidine or lysine, a variety of oxygen donors, for instance, from tyrosine, from a carboxylate group of a glutamine, or also an aspartate, or from a serine. We also have more covalent donors, like a cysteine thiolate, or a somewhat less covalent thioether of a methionine that are all possible. Now, one of the things that I want you to notice about all of these ligands is that in general, these aren't incredibly strong donors. These, of course, are rather covalent. But of course, the cysteine will be both a sigma donor and a pi donor. We'll get back to that later. But in general, all of these support relatively small deltas or 10dqs. Again, we'll look at this picture in more detail later. That means the ligand field splitting is small, and in general, protein active sites tend to go high spin. Okay, so that's kind of a useful thing if you're trying to guess what the spin state is of a protein active site. More likely, those sites go high spin. But there are recently more and more examples of protein active sites that can support low spin electronic structures. And that tends to be not using amino acids, but using other cofactors or using things like CO or CN, as in the hydrogenases, for instance. But in general, of course, the very simple picture we're thinking about, and so this slide isn't meant to be insulting. I hope all of you remember what all your d orbitals actually look like. But the general picture, of course, is to think about how these ligands actually surround our Lewis acid and how they actually then interact with each of these 5d orbitals and how that results in different stabilizations or destabilizations as a result of that interaction. And of course, those stabilizations or destabilizations are going to depend strongly on how we actually arrange the ligands around the metal. And what I'm showing here are just sort of classical complex geometries that one sees in coordination chemistry. These could be 3-coordinate sites that are either trigonal, pyramidal, or T-shaped. And these are the kinds of structures that in coordination chemistry we would expect to see late in the transition series for metals that are relatively d-electron rich. So for instance, in copper-1, we might see these kinds of low coordination environments. Whereas I already pointed out, For copper 2, of course, we're used to seeing a D4H or quadratic planar kind of a coordination environment, whereas in copper 1, that can actually go then tetrahedral. And of course, in iron, we can support a variety of coordination environments, 6-coordinate octahedral, 5-coordinate environments like a C4V quadratic pyramidal, or a D3H trigonal bipyramidal. And all of these are possible, as well as tetrahedral sites. Now, here is just where I want to make another point, sort of looking back at classic coordination chemistry versus what we see in biology and how that kind of inspires. Here I'm again going to use sort of nitrogenase as an example, but what we typically teach, for instance, is that 3-coordinate iron sites don't actually happen in classical coordination chemistry. And nitrogenase is a nice example of where the active site in an early crystal structure actually showed 3-coordinate iron. That's an active site that actually inspired entirely new coordination chemistry. And so there's been a lot of success, particularly by Pat Holland's group, in making what was previously unprecedented coordination chemistry. And so I think this is something fascinating because the bioinorganic chemists continually force coordination chemists to revise their thinking. And that's actually pretty cool, I think. Now, I kept using group theory labels. There's no way in 90 minutes, unfortunately, that we can go through group theory, although it's actually one of my favorite subjects to teach. But I just want to emphasize that obviously group theory relies on having rigorous site symmetry. And that's something that we rarely have in biology. But we can at least approximate a site symmetry. And so these are just examples where you have a certain approximate site symmetry. Here in the iron-sulfur site of rubidoxine, where you can see this is a tetrahedral site coordinated to cysteine. You can also have examples in iron active sites that go really anything from more D3H to C4V to octahedral. And I already commented on this in the previous slide, so I won't belabor this point, but just to sort of point out that really all of these possibilities can happen, and therefore it's useful for us to think about how the differences in the ligand interaction actually impacts the net orbital splitting that we actually see. And so what I'd like to start with is the actual early crystal field model. And so this is from Hans Bethe, really developed in the late 1920s, and it's a picture based on pure electrostatics. So there is no bonding interaction, there is no mixing of orbitals in crystal field theory. What we simply have is a free ion. So here is our Mn plus ion. And it interacts with the ligands, and that destabilizes it. Now, theoretically speaking, if the ligand sphere could be completely spherical, then that destabilization would be fully symmetric, and all the d orbitals would be equal. We know, of course, however, that that is not the case, and that we actually destabilize the orbitals most that are pointed directly at the ligands. Okay? And so I'm showing here, of course, in an octahedral environment where I have 6 ligands. I have 2 ligands along the axial direction, so along my dz squared orbital that will destabilize the dz squared. And it will similarly, within the equatorial plane, if I had drawn an x squared minus y squared here, it would similarly destabilize the dx squared minus y squared. Now, the destabilization of the xy, xz, and yz occurs to a lesser extent because here the ligands are 45 degrees off axis in octahedral symmetry. I also should point out, I made a few corrections to my slides from what was on Dropbox, so I can load them again, but I don't think they're major differences. Now, the appeal of early crystal field theory was really the fact that there were experimental observables that this theory could at least generally reproduce. And one of those was the fact that you could correlate it with the measurement of optical DD transitions. Now, here I'm showing an example of titanium-3, so D1 hex aqua. And so this is what my d orbital splitting actually looks like in just a pure crystal field picture. And what I observe here, around 2300 wave numbers then, was correlated to a transition from a T2G set to an EG set. Now, one of the things many of you will already notice right away is that this is in fact not a single peak. So this is already something that says this simple picture isn't sufficient. And this isn't something I want to go into detail today, but this is just a reminder that when we have an orbitally degenerate state like this, the site symmetry will actually distort to remove that degeneracy. This is known as the Jahn-Teller distortion. That results in further splitting of the d orbitals. In this case, because the electron is in a T2G set of orbitals that is not strongly interacting, that distortion is relatively small. And so what we see here is basically just a shoulder in the UV-Vis spectrum. But in any case, if you kind of blur your eyes a little bit, you can imagine it's roughly a transition at around 2300 wave numbers, and people were happy enough that this reproduced some aspects of crystal field theory. However, there are numerous examples of where crystal field theory breaks down, and what I'm showing you here are really sort of the classic examples that one would normally see in an organic textbook. And that's the very simple example of ferric hexafluoride compared to ferric hexacyanide. Now, if we look at what crystal field would actually predict for this, it would actually predict that the very ionic fluoride should result in greater electron repulsion and a larger 10dq. And so this was something that was a surprise, because from experiment, what one sees is that 10dq for a cyanide is in fact quite a bit larger than 10dq from a fluoride. And so again, just a reminder for most of you, the difference, of course, that we're looking at here is that cyanide is a sigma donor and a pi acceptor, while the fluoride is both a sigma donor and pi donor. And the very important point to remember here is that the nature of the ligand actually matters. It influences 10dq. And that means the experiment cannot be accounted for by electrostatics alone. And we need a theory that actually goes beyond mere electrostatics. The other classical examples for the breakdown of crystal field theory are based on electroparamagnetic resonance. The classic example actually uses iridium hexachloride, but I couldn't actually find the original spectrum in the literature. I could only find reference to it. And the reality is that the story is true regardless of what covalent complex I actually use. But here I'm actually showing for copper tetraimidazole instead. So this is obviously D9. It's an S equals 1/2 system. And if we base things on crystal field theory alone, I should just have an unpaired electron that's not interacting with the ligands around it. The interaction is only electrostatic. And so what I should have is just a free ion G value, just a sharp radical-like signal at G equals 2. And that's not what we see. Instead, what you see is actual hyperfine-like structure, and that hyperfine structure actually reflects the fact that the unpaired electron is delocalized onto the ligands. This is an experimental observation that one can correlate to covalency, and again emphasizes the fact that an electrostatic picture is insufficient to fully capture the actual picture. So this kind of motivates really the need for ligand field theory, and much of this is the developments of von Vleck early on, and this is really a combination of the concepts of crystal field theory combined with molecular orbital theory. And so what it very importantly accounts for is the nature of the ligand donor properties, and it relies on symmetry and covalency to form sigma, pi, and delta bonds within these transition metal complexes. Okay, and so this is, of course, super review. This is going back, I guess, to freshman chemistry now for people. But just a reminder that when we form molecular orbitals, of course, we form both bonding and anti-bonding combinations. These orbitals interacting, if we were forming, for instance, a carbon-carbon bond, would be at the same energy, and this would be a homopolar bond. In the metal-ligand bonding picture, of course, things look a little bit more equal. This would be also, though, for any heteropolar bond, where we form both bonding and anti-bonding combinations, and these could be either sigma or pi bonding combinations or the corresponding anti-bonding combinations. And of course, an important concept that we're always getting out of this is the bond order, where we're looking at the number of electrons we have in bonding versus anti-bonding orbitals to ascertain whether a net bond is actually formed and what the bond order actually is. Okay? So here what I'm basically just showing then is what we would do in the octahedral limit. And so in the octahedral limit, of course, we know that our d orbitals transform as T2g and EG orbitals. Our s orbitals transform as A1g, and our metal p orbitals then transform as T1u. For the ligand orbitals, what we would then do is take the symmetry-adapted linear combination of orbitals and figure out how all of the ligand orbitals actually transform. And so again, in the time we have today, I won't do that. But what you, of course, end up with are various combinations of ligand salts that are of appropriate symmetry to interact with the metal. And just, I guess, some important points to point out here is that the filled ligand orbitals are going to be lower in energy than the metal d orbitals. And the orbitals that we're really thinking about in crystal field theory are the orbitals shown right here. They are antibonding metal-based orbitals. And of course, it's through bonding interactions that some electron density is actually transferred to the ligand. How much this happens, so how big these lobes are that you're looking at on my ligand here, obviously reflects the covalency of that bond. And it really is this MO diagram, and looking at the unpaired electron here that would be in this EG set, where you can see this is not an isolated dx squared minus y squared orbital, but rather an orbital that has a significant component of ligand-based character that explains why we see hyperfine in an EPR for a ligand complex. Okay, so let's just briefly review the kinds of ligands that we actually have and how this impacts the actual d orbital splitting. And so I guess it's kind of most helpful typically to start in the middle here with a simple sigma donor like an ammonia, where of course that lone pair on the ammonia can readily sigma donate into the metal orbitals. And it can sigma donate, of course, in an octahedral environment, most readily to our dx squared minus y squared and dz squared, or collectively the EG set of orbitals. And so what happens in this picture, if we just imagine now here in a very simple picture, I have 2 electrons in a ligand-based orbital that can sigma donate, and here I'm just assuming 1 metal d electron. I form then a bonding sigma-type ligand orbital, and I put 1 electron into the T2g orbital. But it's important to note here that we didn't have any orbitals or electrons from the ammonia that could actually interact with the T2g set. This set thus is non-bonding, and what we see then is only destabilization of the EG set. Okay. The other example, of course, would be something like chloride or fluoride, or, for instance, a cysteine thiolate, where we have a ligand that can both sigma donate, but also has electrons that can pi donate. And this results then in stabilization of ligand orbitals of both sigma and pi type that are bonding orbitals. And now what we get is destabilization of both the sigma bonding EG set, as we had before, and destabilization of the T2G pi star set. And because of this destabilization, what you can see is the net splitting relative to a sigma-only donor has become smaller. Right? It's a relatively simple picture. And on the far side, of course, we have what happens in a pi acceptor, the classic example being cyanide here, or CO. And what's important to recognize here is in cyanide or CO, we have empty ligand pi star orbitals that can actually act as an acceptor. So in this case, what happens is just as before, we have a sigma interaction that stabilizes the ligand and destabilizes the metal. But now we actually have a ligand pi acceptor, and that ligand pi acceptor will become destabilized, and the metal-based orbital becomes stabilized and bonding. And so now if you look at what happens to 10dq across the series, or our delta value, you can see it becomes larger as I go from a pi donor to a sigma donor to a pi acceptor. And this is readily explains the difference one sees between 10dq for fluorides and cyanides, and something that you could not have explained based on crystal field theory alone. And it is this concept out of ligand field theory that actually explains the spectrochemical series. And here I'm just showing this as a reminder that we can sort of group ligands based on the observed delta, be it small or large. And you can also do this then biochemically for bioinorganic theories and look similarly at how the splitting that you see from different amino acids also is based on their ability to sigma or pi donate. One thing that's notably absent really on this spectrochemical series, which actually was originally published by Andrew Thompson, are ligands that support a large delta. And I would actually say, because at the time there weren't so many biochemical examples that were known, but now we're seeing, of course, many active sites that can incorporate CO and CN, and then that, of course, would also be on the far side of this biochemical spectrochemical series. Okay, so let's actually just talk a little bit about high spin and low spin complexes, because that's some of the useful information we can get out of actually knowing the magnitude of delta. And so I'm starting here just with a D5 electron configuration, so what we would have, for instance, in a ferric active site. And we can, of course, populate these d electrons to arrive at an s equals 5/2 ground state or an s equals 1/2 low spin ground state. And really, it's the balance of the ligand field splitting and the energy it costs to actually spin pair that determines which one of these is actually my ground state. And so provided that delta is actually relatively small, then the cost of energy to actually spin pair is too great. This is, of course, the case when you have a weak field ligand. When you have something like fluoride, for instance, then you will favor this high spin-like configuration. At the limit, however, when delta becomes too large, it's more energetically effective to actually spin pair than to promote the electron to the next level. And this, of course, then results in a low spin complex. Okay, so let's talk a little bit really about the utility of this MO-based picture, because I think these pictures are only useful if they somehow help us calibrate our thinking. And I think a nice example is just to think about an MO diagram for just a hypothetical transition metal oxo complex in C4V symmetry. And so this is just a partial diagram where I'm just trying to reflect the interaction of the metal d electrons with the oxygen 2p's. And so here, my oxygen 2p's are all filled, and that forms this sigma and pi combination. And in C4V symmetry, my dxy would be non-bonding, and then I would have a pi star, the pi star disappeared somehow, dxzyz combination, and a sigma star dx squared minus y squared. Now, in the case of having a D0 complex, we can look at what our bond order is. And of course, I have 6 electrons occupying bonding orbitals in this picture for the M oxo unit. And I have nothing in the D orbital. So this has a bond order of 3. Now, if I think about populating it with 1 or 2 electrons, so going up to, for instance, a D2 manganese 5, I put those 2 electrons in a non-bonding orbital. That means it doesn't affect the net bonding interaction. And what's important about this is that means when I form a manganese 5 oxo, that typically is going to be a triple bond. It's actually going to be a very stable complex, typically. So this is actually why there, in terms of high valent crystal structures, you do actually see more for ones that actually form triple bonds. They will be stable, they'll be short, strong bonds, and they tend to be then fairly unreactive. Okay? So what happens then as I start to populate some orbitals with anti-bonding characters? So for instance, if I go to a D4 iron 4 system, I put 2 electrons in the non-bonding, but now I put 1 electron in each of my pi star orbitals. And that starts to lower the bond order. And what we see is that still a bond that forms. It still has a bond order formally of 2, but it is going to be a more reactive species. And that's probably why we see things like iron 4 used as intermediates in biology. In fact, manganese 5 is often invoked, actually, in the photosystem, but that is a point of big controversy, especially among many coordination chemists. And there's sort of a question, and maybe this is a coffee break game to play, what coordination geometry would you need in manganese 5 to actually possibly still make it a reactive intermediate? Okay. But the other important point to make here as we look at this MO diagram is that when we reach D6, we actually have no net bond. And this is what Harry Gray often refers to as the oxo wall, and the idea that late in the transition series, you typically don't see metal oxos. Now, this has been proposed, so there are papers reporting platinum and gold oxos, but this remains a subject of great controversy. And I'll also say that many people do invoke these as sort of possible intermediates that could be very important, for instance, in oxotransfer, right, that you basically end up then breaking that bond. Okay, but Frank isn't here, and so I had to steal Chris's joke. Chris was actually famous for using Frank Neza quote bubbles while he was at the CEC, and I'm sorry Frank couldn't be here because there's always great take-home lessons from his talk, and I know that the one thing he would really want me to communicate to you is that orbitals are not observables. So as much as we like this picture as chemists, and I really like it, it's a picture that I feel is very intuitive, I'm happy and at home with it, it's in spectroscopy, of course, not really what we see. And so this is now taking us back to our first slide. And of course, what spectroscopy really involves, no matter where you are in the electromagnetic spectrum, is the transition between states. And orbitals, sadly, are not what we're observing. And so here, I actually want to take the time just to group the spectroscopy that we do into two major types, the sort of ground state and the excited state spectroscopy. And I'm doing this actually taking inspiration from my former PhD advisor, Ed Solomon. And this is actually a diagram from a paper that I wrote together with Nikolai Leonard, one of your other teachers this week, when we were both in Ed Solomon's group. And this was a review article on spectroscopic methods, but the general idea here was that if we look at something and we take Ed Solomon's favorite complex, which is copper tetrachloride, I think he's done every possible kind of spectroscopy you could do on copper tetrachloride. What we really see here is that this energy level diagram, it spans 10 orders of magnitude in photon energy. And we can use different kinds of spectroscopy in the valence region or deep in the core region to get different insights. But the very important message that I want to give all of you is that ultimately that should all form a cohesive picture. And this, I think, is really one of the big strengths of the bioinorganic community, the fact that techniques are applied that span this whole energy scale. But of course, we have to always be careful and think about what it is that we're actually looking at. And are we probing a ground state, or are we probing an electronic excited state? And so these groupings aren't rigorous, but they're groupings that at least help sort of sort out one's thinking. So what do we mean when we talk about ground state methods? And when I say ground state method, what I mean is the electronic ground state. And so that's at relatively low, from 10 to the minus third to just tens of wave numbers. And what we're doing are probing transitions that correspond to very small changes in energy. And so what I mean by this are just splitting of magnetic orbitals. So for instance, the splitting of an s equals 1/2 ground state into m sub s of minus 1/2 and 1/2 levels. And so in a simple picture, you could consider ground state methods, things like electron paramagnetic resonance, ENDOR, ESIM, and Mossbauer, where you're looking at just changes in nuclear states that are actually being split. Now, on the other side, we actually have excited state methods. And so here, of course, we're at higher energies, something like 0.01 V to maybe 100,000 eV, depending on what element specifically you're probing. These could be things that are from the near IR to the visible. And so the electrons are excited then from occupied to unoccupied valence orbitals, resulting in the observation of different states. These could be ligand field D to D transitions, for instance, CD and MCD. Or we could look at visible. Here we'd be looking at ligand to metal charge transfer, metal to ligand. One could also look at absorption, CD or MCD in this range, and resonance Raman. And then finally, excited state methods, of course, cover my favorite methods, which are core excited states, like X-ray absorption or the inverse experiment X-ray emission. And so basically sort of the general message here is that when you look at an excited state method, this involves electrons transitioning from occupied to semi-occupied or empty MOs. And this is what, as chemists, we do relate back to an MO-based picture. And so I want to say that isn't wrong. One just has to sort of then ask what state that corresponds to. As I've already told you from Frank's picture, it is essential to understand that the orbitals aren't the observables. You always observe the many electron states, and this is probably how you were taught UV vis, and for many people it probably scared you and then you never thought about it again. And so we're going to briefly review that and at least show examples where that actually is useful. And in ground state methods, you are, of course, focused on magnetic dipole transitions between either nuclear or electronic spin states. And since we, in the orbital picture, remain in electronic ground state, I think a lot of times when we use these kinds of methods, we tend to throw out a state-based picture and sort of not think about it too much, at least in terms of assigning term symbols. And so you can kind of think of this also in terms of term symbols, and we'll get back to how you actually assign term symbols in just a minute. But if we take something like copper 2d9, and so this is a doublet, e.g. ground state. I have one electron hole in the EG set, and that corresponds to a doublet EG. In a ground state method, then this term symbol is unchanged, whereas for an excited state method, if you think about your d orbital occupation, I end up here with instead a hole in the T2G set. This is a doublet T2G, then excited state. And so I actually transition from a different term symbol. Okay, so that's basically how I'm grouping these spectroscopies, whether or not my electronic term symbol has actually changed. Okay, so really for spectroscopy, we actually only need a few selection rules, and this is what I want to today go through the derivation of and just remind you of what they actually are. And so for excited state methods, we basically have three important selection rules: the delta S equals 0 spin selection rule, the parity selection rule that says we can only do G to U or U to G, and then the dipole selection rule. The parity selection rule, of course, relates to this, but only at high symmetry limits. And then we have, of course, ground state methods where we look at a change in M sub S or a change of M sub I. Okay, so this is just a reminder that for the most part, for the first row transition metals, we work in a Russell-Saunders coupling limit. The JJ coupling limit isn't really used very much in inorganic chemistry, although one will see that for heavier transition metals, and also, I think, more dominantly in physics-based literature. And so here, what we're focusing on basically is a term symbol that we assign as a 2s plus 1 L term symbol. And here, L is actually the total angular momentum for the entire system. So we would have L's of 0, 1, 2, 3, and so on, corresponding to SPD F. And then S here is just the total many electron spin angular quantum number, or the multiplicity. Okay? And so these are just simple examples. Here I have one electron, so 1/1/2 electron, 2s plus 1 is 2. I take the highest M sub L, which is 2, and that gives me an L of D. So this is a doublet D. In this case, where I have an S equals 5 Hess system, I have a multiplicity of 6 and an L of S when I sum over 2, 1, 0, -1, and -2 to get my total L value. I'm kind of assuming that most of you have all seen this before, and that's why I'm going through it relatively quickly. Okay, so this is not something I will go through slowly. How many of you did microstate diagrams at some point? Wow, what if not more? It's like a special kind of torture. Have a few beers, and then you can work this out for like a D3 system. But for now, I'm just going through that. The reason, to me, this is the reason that chemists like orbitals, right? Because what I'm dealing with here is a very simple case of just 2 electrons in a p orbital. This is carbon, okay? Like, this is really simple. And yet, if I look at all the ways I could place 2 electrons in 2 orbitals, I come up here with all the possible M sub L and M sub S states, and already I have 15 possible microstates. And so it's something that we don't like to have to do every time we think about what possible excited states I actually could have, right? So, but anyway, when we see all of these microstates then need to be grouped further in order to determine what term symbols actually make up the many electron states of a P2 configuration. And so what one does is to group these by their M sub L and M sub S numbers. So I've done groupings of these 15 terms by their variation in both m sub s in this direction and m sub l in this direction. And then what we do is we just choose the highest m sub s and m sub l for the parent microstate. So that would be the m sub s of 1, m sub l of 1. That gives me an L of 1 and S of 1, and a range of m sub s from 1 to minus 1, and m sub l of 1 to minus 1. This gives me 9 microstates that make up my ground state term, which is a triplet P. We would then do this for the rest, and I've just put little colored blocks so you know what they are. But what I end up with then are 3 different term symbols. These are the triplet P, singlet D, and singlet S, and these are ordered by Hund's rules. So basically, the terms of any configuration with higher S are going to be lower in energy. And also the terms with a given configuration and equal spin, the higher L will be lower in energy. So basically, the triplet P then is lowest, but singlet D has a higher L, and so it's lower than the singlet S term. And this all comes from atomic spectroscopy. So this is why I think that oftentimes we feel a little bit of a disconnect. But we're going to talk a little bit more later about the derivation of Tanabe-Sagano diagrams. But basically, what I'm showing here is just in the atomic limit, in the spherical limit, we're on this side deriving our atomic term symbols, and we haven't yet added a ligand field. That's important to realize. But basically, I just want to emphasize that when we just get to the D2 limit already, things become a lot more complicated. So this, for example, would be hexaquavanadium-3 with 2 electrons in the D shell. And so there are, of course, simple formulas to figure out the number of microstates you have. That goes as 2 times the number of orbitals factorial divided by 2 minus the number of 2 times the number of orbitals minus the number of electrons factorial, number of electrons factorial. And what that gives you is for only 2 electrons in 5 orbitals, you already have 45 microstates. And so that's the reason that why most of the time, unless you're Mikhail Atanasov at our institute, who somehow has memorized every Tanabe-Sagano diagram there is, the average person can't actually tell you this without typically looking up these diagrams, unless you look at it all the time. But what I will show you later is that these can be very useful, at least in terms of calibrating our thinking when we look at spectra. But let's just talk a little bit more about how we actually get these spectra. So in this limit, in the free ion limit, before we've brought in a ligand field, we're basically just ordering things in units of electron repulsion. And this is why that the highest spin term actually will be lowest in the free ion limit. And then as we bring in a ligand field, and that ligand field becomes larger and larger, then the ligand field starts to dominate, and the electron-electron repulsion can be treated as a perturbation. So in cases where you actually go from low spin to high spin, there's some critical energy where that change actually occurs. Okay? And I just want to point out that, of course, delta is the increase in ligand field, and beta here is the nepheloxetic reduction. So what happens as covalency increases, the B value becomes reduced from the free ion limit. Okay? And so for highly covalent complexes, B becomes smaller and delta over B becomes larger. And we'll talk more about why that matters in a bit. Okay, so let's just look at some examples in spectroscopy in terms of how this might matter. And we're going to use the simple example of UV vis, and then you can apply this to other things later. But basically, as I said before, we're looking at going from a ground state to some excited state, and we're looking at the interaction of our light passing through our sample according to the Beer-Lambert law. Right? So we're looking just at absorption related to a molar absorptivity. Okay. So here it's important to ask, when we do this, what transitions do we actually observe? And the transitions we observe can, of course, be within the D shell. This is DD excitations, or they can be more energetic transitions, such as ligand to metal charge transfer, metal to ligand charge transfer, or at still higher energy, intraligand excitations or ligand-ligand excitations. And all of these are possible. You can sort of visualize them instead. This sort of just visualizes kind of what one expects with a DD transition here versus an LMCT or MLCT. And here we have a pi star transition within a porphyrin. But the question is how do we know what can happen and when? And this comes back to group theory and selection rules. Okay. And so here I just want to go back. We already talked about assigning atomic term symbols, and we also need to, of course, assign molecular term symbols. So maybe I should just go back. On this side of the Tanabe-Sagano diagram, we're at the atomic limit. And at this limit, actually, once we've applied a ligand field, you'll notice that we transition from atomic term symbols to molecular term symbols. And those are molecular term symbols all in OH symmetry. And Tanabe-Sagano diagrams can be modified for lower symmetry, but that's also then an added complexity. But the nice thing is that regardless of the symmetry, we can always use group theory. And I guess that's another question. I'm just testing if you guys are still awake. How many of you had something that looked like what's on this slide in terms of group theory applications in spectroscopy at some point? Okay, not everybody, certainly. Okay. So what I want to show here is just how you go about determining a allowed transition. And to determine what an allowed transition is, you need to know actually the symmetries of what's actually involved. And here, the total symmetry of a state follows from the direct product of the singly occupied molecular orbitals. And what we need to do is to be able to always assign a term symbol for a given many-electron either ground or excited state. Okay? And so a simple example would be a D4 configuration in D2H symmetry. And here we would have singly occupied MOs that would have one electron in them. These would be the AG, B1G, B2U, and AU. Notice these small letters refer to molecular orbitals. Okay? What I would do then is to actually take the cross product of these, and you can do this using a D2H character table, but here I'm just giving you what these cross products actually are. And what we find then is when we take AG cross B1G, we get B1G. B1G cross B2U gives me B3U, and B3U cross AU is anything cross A gives back itself is the B term, and here we have a U cross U, which gives G. So this is B3G, and then we just need to work out the multiplicity, which in this case ends up being a quintet state. Okay? And we could do the same thing, for instance, for a D5 in octahedral. Here you could also just look it up from a D5 Tanabe-Sagano diagram, but this is one that you probably should know. So we have a symmetric, half-filled, high-spin shell, multiplicity of 5 halves, or a 2s plus 1 of 6, and this is a sextet, then A1G ground state. Okay. So I want to keep this example as simple as possible, and what I'm showing here is now just a character table for D2D copper tetrachloride. Okay? And basically what you see here are the symmetry elements and how they actually transform. So you could actually look at this character table, obviously, to see how my d orbitals actually transform. And I'm showing here for the ground state, my z squared transforms as A1, my x squared minus y squared is B1, and so on. And if I populate this, none of the filled orbitals actually contribute to determining my term symbol. So all I have to do is see that I have one unpaired electron in the B2 level, and this is a doublet B2 ground state. Okay? This is a relatively easy example to pick. Then the first excited state would be promoting an electron in the E set to the B2 set, and that would give me a first excited state. That's doublet E. Now the question is, how do I know if I'm going to observe this transition or not? And whether or not I observe these transitions actually, of course, depends on the selection rules. And so here, I want to briefly just review. Wow, that was like, you know, the funny thing is I've looked at Frank Nace's slides. I removed almost all the equations, and then these are the ones I added from my my own notes, and it took me a long time to do it, so don't moan. I'm a spectroscopist. I'm not very good with equation editors. But anyway, so this is just a reminder that theory and experiment are connected through the oscillator strength, right? And so our oscillator strength is just basically integrated over all of our observed extinction coefficients at every frequency, right? So that's something that we observe. Now we need to actually relate that to something in theory. And in theory, what we relate to then is the integral I'm showing here, where we're looking at a ground state wave function, an excited state wave function, operated on by our electric dipole operator, which I'm showing here as mxyz. And so for this actually to be non-zero, what we need is that, of course, the oscillator strength to be non-zero means that this triple direct product has to be fully symmetric. And in group theory terms, that means that it has to be non-zero. Okay? So now what we need to do is operate on this with our magnetic dipole operator. And we need to remember that the magnetic dipole operator transforms the xyz coordinates. And so what that means actually is that it actually operates only on the orbital component and not on the spin component. Okay? So we can actually then rewrite this as a triple direct product and then just this direct product of the ground state and excited state wave functions. Okay? Now from this then, the spin selection rule then is really easy to understand because I have two things that when I multiply have to be fully symmetric. And what that tells you is these two things have to be the same. And that means that only transitions between like spins are allowed, right? So I have to have a ground state wave function that I can represent as some irreducible representation with a certain spin, excited state with some irreducible representation of a certain spin. And if these two have to be equal, delta S has to be equal 0, meaning only singlet singlets are allowed, triplet triplets are allowed, and singlet triplets are forbidden by the selection rule. Okay. And the variation, of course, then is the orbital selection rule, or what is known as the Laporte selection rule. Here I have a triple direct product that has to be non-zero. So what this means is the irreducible representation that represents the symmetry of my ground state and excited state times the dipole operator has to be non-zero. If I look in OH symmetry, so if you looked up a character table, looked on the far right-hand side, saw what transformed as XYZ, you would see that's T1U. And that means that the product of the ground state and the excited state also has to transform with U symmetry. The only way for that to happen is to have either a ground state that is G and an excited state that's U, or a ground state that's U and an excited state that's G, in order for this to be totally symmetric. What this means is that transitions between states of like parity are forbidden. Why do you care about that? Because we've just spent this whole time talking about D to D transitions. And recall that in tetrahedral, they transform as T2G and EG, meaning that D to D transitions are formally forbidden by the Laporte selection rule. And this is an important selection rule to remember. Okay? So this slide basically just summarizes these selection rules and basically is a little bit of a reminder. I don't know why I'm walking so much. I'm keeping myself away. I'm slightly jet lagged. I'm not sure what coast I'm on at this moment. I flew in the day before yesterday to Seattle from Germany and then back this way. So anyway, but this is basically a summary of everything that I've just told you about selection rules. So I guess I should point out that the spin selection rule is a strong selection rule, especially for first row transition metals, which is what we're mostly focusing on bioinorganic chemistry. Beyond the first transition series, the spin-orbit coupling becomes significant enough that you can break the spin selection rule. The orbital selection rule is what we would refer to as a weak selection rule, and that means that, of course, this doesn't matter if something breaks the symmetry. So if I go from octahedral to tetrahedral, by group theory, I lose inversion, and the Laporte selection rule breaks down. Okay? Yeah, I think I'll keep it like that. The other important selection rule, and I would say this, especially for my group, is always important, is this delta L selection rule. And although this, in many ways, has a relation to the Laporte selection rule, rigorously speaking, This comes out of quantum mechanics and the Wigner-Eckert theorem, and basically says that S to P or P to D is possible because delta L has to be plus or minus 1. And this then follows that either D to D, S to S are all dipole forbidden. Okay. So what does this mean? Of course, we say things are forbidden, and that doesn't mean that you never see them, obviously. It just means that you see them with varied intensity. And so typically, if we just sort of, for comparison, look at a ligand to metal or a metal to ligand transition, this is electric dipole allowed, and so when we look at it in the optical absorption, it will have relatively high extinction coefficients on the order of hundreds to over 10,000. Parity forbidden transitions, though, are going to have relatively weak intensity, so something less than 500 per molar per wave number, and spin forbidden are going to be even smaller. They're going to be incredibly weak. Okay? So now that you've sort of seen where these selection rules actually come from, I want to go back to the example that we already looked at together of D2D copper tetrachloride. And what we already described based on group theory was what our ground state is, what our excited state, first, second, and third excited states are. And so now what we need to know is when I basically multiply my ground state wave function by my excited state wave function, is it equal to a dipole operator? Okay. Now what I already told you is the dipole operator transforms as X, Y, or Z. So in a D2D point group, if we look here, what I see is, what I see is not much, that D2 transforms as Z, and the E component transforms as XY. Okay, so the dipole operator doesn't have to hang out all together. This is actually what gives you polarization dependence. Okay? And so what we see here is if I multiply a ground state by excited state wave function and end up with either B2 or E, I know the transition's allowed, and I also know what its polarization actually is. So if we take this example and I take B2 cross E, so I'm basically just multiplying this line times this line, right? And so I have 2 times 1 is obviously 2, minus 1 times 0 gives me back the 0, and if I just follow that across, you can readily see I get E back. So I get back a transition that actually is XY polarized. In contrast, if I take B2 cross B1, what you end up seeing is I actually end up getting A2. A2 doesn't transform as either of the dipole components, and this transition becomes forbidden. Okay? And then I could do the same thing for the last example, taking B2 cross A, and I would find that it's actually Z polarized. And so this gives you a way to use relatively simple concepts in group theory to actually ask what it is that you would predict. And so these are data from the original Ed Solomon paper. For D2D copper tetrachloride, unfortunately, these aren't polarized data. But what you do see, as was predicted, you see 2 features. And that's most clearly seen in the low temperature absorption. It smears out a bit in the dotted line, which is the room temperature absorption. But I personally find this super satisfying. We saw something that looked like an abstract mathematical exercise, but it results in a real observable. And so that, to me, is exciting, but that's probably why I'm a spectroscopist. And what we see then as we go from D2D copper tetrachloride, as we go from this distorted site and we force all the ligands into the plane, we expect to actually raise the energy of certain transitions, and that's exactly what we see, because here the energy scale is actually going in this direction, and we see that shift in the actual transition. So this is a real group theoretical manifestation of what this change in coordination geometry actually, or point symmetry actually does to an actual spectrum. Okay, so let's take a look at a slightly more complex UV-Vis spectrum. And here, again, I'm going back to the vanadium-3 hexaqua example that I already showed you. And here, what we basically can do is go back and use that Tanabe-Sagano diagram that we already talked about. We go from our atomic weak field limit to a strong field limit. We, of course, only have 2 electrons here, so this won't do a spin crossover. It has to always be high spin. But what happens instead, as I increase the ligand field, the energy of the lowest energy excited states in general actually increases in energy, right? So, and what we see then is our lowest energy allowed states are transitions to triplet T terms. And that's what these are. Okay? Now, there's one thing here I'm ignoring in this Tanabe-Sagano diagram, for those of you who are fixated and really looking at it, right? And that is this transition right here, this low-energy singlet. Now, I already told you that's spin forbidden, but what's interesting to note about it is it's not just spin forbidden, but it doesn't change as a function of ligand field, right? It always stays the same. And that's because this is an inner shell spin flip. Doesn't matter how big the ligand field is, I'm just flipping an electron up and down. That costs me energy, but it doesn't depend on the ligand field because it's all within the P2G manifold. Okay, let's look at some more complicated ones, right? This is fun. Nobody's going to drink a beer with me. Okay. But what I want to look at here is, this is a Tanabe-Sagano diagram for D6. So Anselm in my group spends a lot of time staring at these, so he can walk you through these in detail. But here what we're actually seeing is the lowest energy here is, if I were going to draw it out so it didn't look so messy, it's this quintet T2 to quintet E transition. So it's actually quite simple, right? And this would be my lowest energy transition that could already tell me something about 10DQ in a ferrous complex, right? So that's useful. There are many other higher lying states. This is actually obviously the point where I do my spin crossover, right? I go from high spin to low spin at some point. But I think what's interesting about this diagram, so keep this in mind, this is my ferrocite, and I have this clear low energy transition. When I go to ferric and D5, I open up this hole in the diagram, this very pretty hole. And what's happening here, of course, is now I'm at the limit of being low spin D5. And so every transition here is spin forbidden. Okay? And so instead, what's happening here is that this lowest energy transition is now to a quartet state. And the reason this is so much higher in energy than ferrous is because to reach this quartet state, I have to do a de-excitation and spin pair. And that costs energy. Okay? And I think this is a really beautiful example about how a relatively simple concept in coordination chemistry manifests itself in real spectra. Okay. But as beautiful as this is, we're often like hunting the literature to find examples where you see this kind of rich absorption spectra. This is actually something that motivates a lot of research in my groups that I'll talk to you about, because we now have experiments where you can see D to D spin forbidden transitions in an allowed way. It's something we're super excited about. But normally, the optical spectra is often quite limited because these D to Ds are forbidden and spin transitions are forbidden. And then I measure a bioinorganic system. I look at a protein and like, what do I see? Woohoo, 280 band, right? And so it becomes so dominated by the amino acids, especially tyrosines and tryptophans, that a lot of times what I'm showing here is just a difference between a copper protein and its apoprotein. So the copper is there in red and the apoprotein's in black. So the blue is the actual different spectrum, right? And it has differences. The copper contributes to the spectrum. But the detailed analysis is challenging. And this is the reason why we want to do other kinds of spectroscopy. And this is the reason that you're all here. As biochemists, you could already find out everything you wanted to know from an absorption spectrum, then we wouldn't be having nearly the fun that we're going to have this week. And so with that, I was planning to actually just do sort of a brief run-through of other spectroscopic selection rules, but I think instead I'm going to just stop here with basically a summary of what we can sort of take from most spectroscopy. I've gone through the selection rules, and this is just kind of a summary of what you should remember about excited state and ground state methods as you travel through this week and try to think about whether a transition is allowed or not. And with that, I would like to thank you for your attention, and special thanks to Frank Neza, who wasn't here but let me steal slides. Also to Chris for stealing jokes, and you for your attention.
Well, thank you, Serena. One thing I forgot to point out is if you have any questions in between, we try to have this interactive where, there's a think this was a perfect survey, and I think a great summary of what's setting the stage, what's to come. But I think upcoming talks, there might be more pertinent questions. If you are not getting stuck on something, this is really supposed to be interactive, and so that likely you won't be the only person getting stuck. And so please feel free to raise your hand and ask questions in between. Are there any questions on this now? Yes.
It's not particularly actual. So you talked about the Fimoka today.
Yeah.
Carbon center.
Sure.
And I'm afraid that I may not be asking to the right person here, but I will still ask it.
Yeah.
The question is, what is our current understanding of the coordination of the carbon around the 6 irons in the Fimoka center?
I mean, it's a mu6 coordination, and all of the irons are at roughly 1.95 angstroms from the carbon.
Is there a theory that can explain the carbon coordination there?
I mean, I think that this is not. I mean, I think that often people are disturbed by this, but because it just seems so strange. But there's actually precedent for it in other organometallic compounds. So, iron carbides with mu6 or iron clusters with mu6 carbides are known in the organometallic literature. They typically have carbonyls as opposed to a central carbon. But it's, yeah, I mean, it is, in some sense, a coordination compound that, in that sense, has some precedence. But, and these are, I think you have to be careful how you think of the bond order. And how well we actually know the force constants between those bonds, I would argue, not very well at this point. There's been a little bit of NRVS by Steve Kramer's group to try to pull that out. And there have also been computational studies trying to get bond orders, but there's large discrepancies in those values. Yeah. Yeah.
I'll also ask a specific question. You mentioned the reactive state Q of methane, soluble methane monooxidase.
Yes.
Do you guys have an opinion?
Do we have an opinion? Of course.
About that short iron-iron vector. I simply believe that will not hold up to further experimental scrutiny.
I agree with you.
Okay.
But it's in the literature, so it has to be refuted before we. Yeah.
I have a question about the how to distinguish between high versus low spin centers. So you've made it clear how we can classify the ligand field.
Yes.
But how does this relate to the nature of the metal? Because I'm guessing that it's also influenced by the nature of the metal. For example, a molybdenum center would be a low spin species, whatever the ligand is.
Yeah.
And so how do they connect to one another?
Sure. I mean, obviously, most of what I was focusing on was really as it relates to the first transition series. And obviously, for the second or third transition series, the ligand field splitting becomes such that low spin states are almost always favored. I was focusing on the first transition series because that's most of what we talk about in bioinorganic chemistry, save molybdenum and a bit of tungsten. But for the most part, in the first transition series, you do have quite a bit of flexibility in spin state, and there are subtle factors that actually govern it. And I think that's a particularly important point in bioinorganic chemistry, where we often even discuss in terms of reaction intermediates the ability to access two-state reactivity, and how close in energy different spin states actually are can enable different reaction pathways. And that's something that's really important here and probably less important in heavier metals.
Would you go a sentence or two past the last thing you said about reaction?
A sentence or two past I was talking too fast. I didn't count my sentence.
To say a little bit more about you're talking about reactions or something?
So I'm saying that I believe the accessibility of different spin states is particularly important in bioinorganic chemistry, particularly, for instance, in high-valent iron chemistry, where there has been a lot of literature that has invoked two-state reactivity and reaction pathways, meaning that, for instance, you might proceed on a triplet or a quintet pathway, depending on the mechanism of the reaction. And so that means the ability to populate higher orbitals with electrons actually can matter in terms of the ability, for instance, to cleave a metal oxo bond or,
Yeah, that was the last thing you said. That was past. I needed you to go there. Like, how did it connect?
okay. Is that still not clear then?
No, it's pretty good.
Okay.
Close.
Okay. Coffee time?
I think the crowd is waiting for coffee.
I think so too. Okay.